I want to begin with a caveat by saying that I can only really speak to this realm in terms of the sort of paleo data model comparison side of things, and I know that there's a whole sphere of there's a whole sort of topic in the space on observational data model comparisons that I think Jess and Adriana and Jesse also covered a little bit of in their presentations. And so if by the end of this we feel like there's still a lot more that needs to be addressed, maybe we can think about how to do that in subsequent presentations. But what I'll really be focusing on here are reconciling sort of paleo data model comparisons, and I think that some of that has applications to the modern observational field, but yeah, I'll really be focusing on the proxy side of things. So, but I do think it's interesting that paleo data model comparison is a really big and rapidly developing field all on its own, and it has particular relevance within the water isotope community because most paleoclimate records are based on water isotope ratios through archives like corals, stalagmites, lake sediments, trees, and ice core records. And these archives really help us understand our climate system at a much deeper level than what we have access to from the instrumental period. And they also allow us to sort of contextualize and quantify anthropogenic trends in our climate system. So let's move forward. So I think water isotopes are really unique in the sense that I think of them as sort of the connective tissue between each of these sort of primary tools that we have to understand our climate system, namely theory, models, modern observations, and paleoclimate proxy records. Each component of this system informs the others, and therefore the tools that we have to make these comparisons between these realms are really important and have been moving along quite rapidly in recent decades and years. There's a few things I want to sort of touch on to start out with. So these data model comparisons in the observational sphere are really important for things like assessing accuracy of model parameterizations, which we've talked a little bit about in previous presentations, things like water vapor measurements that can help parameterize large-scale convection, and also for process-level studies. But they also inform our interpretation of proxy records. For example, how we understand isotopes in precipitation and isotopes in seawater. Paleoclimate data model comparisons are really critical for interpreting our paleoclimate records, including some of our basic assumptions about what we think our proxies mean. They're also critical for understanding the sort of dynamical context behind the climate changes we reconstruct from proxy records, and for testing some of our hypotheses that are developed from theoretical principles and model simulations beyond what we can really do with a modern period. And this is important because, as we're moving into an increasingly uncertain future, that's very different from what we've experienced in the last 100, 150 years or so. We need to be able to sort of understand a range of climate states and climate feedbacks that are different from what we've seen. But there are a number of challenges to making these data model comparisons. And some of those include the fact that this is from Jesse had described this previously, that existing modern isotope records aren't ideal for model development and validation because they're often too sparse or too short, or they don't pick up on the quantities that were really needed for model development. In the proxy realm, we have typically better temporal coverage, but much worse spatial coverage. So we're often dealing with very sparse observations that can be high resolution or low resolution and have sort of very different temporal and spatial coverages with very different biases, and I'll get into all of this in a bit, but there's lots of challenges in dealing with different types of proxy records. Another aspect is when we're trying to do things like compare GCM output to proxy data, downscaling that data to the sort of local scale that a proxy record or instrumental data records. And then also making apples-to-apples comparisons between model output and proxy data is a real challenge. Okay, so now I'll touch on a few current tools and recent developments that have come about in the paleo data model comparison realm. So the first is an increasing number of isotope-enabled climate models, and this includes general circulation models, which Jesse introduced. So in the last, so at the moment, the isotope-enabled fully coupled GCMs include HADCM3, GIS, MPI, and recently the Community Air System model, and then there are also a number of models that are currently in development. But you know, building upon sort of a model hierarchy, it's particularly useful to build into this context idealized and intermediate complexity models, and folks like Sylvia D has been doing quite a lot of this through SPEEDY, the isotope-enabled version of SPEEDY, and Adriana Bailey, I'm sure, can speak to things such as the 1D zonal mean mass balance model that she's put together. And then also things like regional models, and I'll show some results from Sam Stevenson, who's done some really interesting work comparing coral proxy data to isotope-enabled regional ocean model. So this sort of model hierarchy is really important for developing both robust paleoclimate interpretations and also to sort of understanding the dynamics behind those. And then secondly, we've also seen a real increase in the sophistication, breadth, and application of some of the tools that really bridge the models to the, or the sort of the output from the models, including water isotopes in those models to the proxy realm. And so I'll go through some of those briefly. Well, actually, let me just mention them. So I'll go through proxy system models, pseudoproxy experiments, and paleoclimate data assimilation techniques, which I'll just touch on very briefly. I think we're going to have a presentation on data assimilation later. Okay, so I just wanted to highlight, I think, a really useful review article that came out last year by the Hydro 2K consortium that was headed by Jason Smearden. And it was on comparing model, proxy and model estimates of hydroclimate variability over the Common Era. And I think one of the most useful aspects of that paper is that they outlined some basic guidelines for making robust model data comparisons. And so these include really trying to leverage the disparate and complementary strengths of both information sources, both the proxy reconstructions and the models. And so acknowledging that paleoclimate data are incomplete climate system indicators, and that at the same time climate models often contain large biases, or can have poorly resolved physical processes, among a number of other things. And so it's really about trying to find the common space and the ways that each set of information can inform the other. And then it's really important rigorously assess and quantify the uncertainties and the limitations of models and proxy data. And that in order to do that, in order to make these really robust comparisons, this needs to be made on sort of equal ground, these apples to apples comparisons. And so a big part of that is moving, the model output into, water isotope space, but then how we get the proxy data, the proxy observations to be on par with model output is sort of a whole nother field. And one way that we can do that, one I think of a really emerging way to do this sort of on par comparisons is through data assimilation techniques. And so I'll speak a bit more about that in a second. So yeah, just coming back to this paper, I would recommend it if you guys are interested in knowing a little bit more about this as it relates to hydroclimate reconstructions over the Common Era, but I think it also just has some really useful information about proxy model comparisons and water isotope space in general. The Common Era is a really sort of opportune case study to think about how to create these optimal data model comparisons, because it's a period in which we have some of the most sort of extensive and high resolution proxy reconstructions, and we also have a fairly extensive set of transient full forcing last millennium model simulations, including ensemble simulations, and so it really provides an opportunity to make these comparisons, or to develop a framework for making these comparisons really well. Okay, so let me just touch now on introducing pseudoproxy experiments. So I think this is a nice place to draw from kind of through the Common Era framework, because they're particularly useful for these sort of large global or large-scale networks of proxies that come from multiple proxy records. And they're really controlled experiments that use model simulations to test the performance of different types of paleoclimate reconstruction methods. And so, so this review article by Jason Smearden, I think, is a good place to go to kind of understand how these pseudoproxy experiments work. But they're really motivated by the fact that paleoclimate reconstructions, especially these ones that draw on networks from a large number of disparate types of proxy records, are really the product of a number of different uncontrolled factors, and it's really hard to isolate the impact of a particular one of these uncontrolled factors on the total reconstruction product. And so it provides a context for really making controlled experiments to test different components of the reconstruction framework and assumptions. And so just an example, this is from this review paper that was looking at global temperature reconstructions over the Common Era, over the last 1,000 years, and kind of coming back to some of the first multi-proxy reconstructions to do this was from Michael Mann in 2009. And so going back through sort of this full suite of paleoclimate data set that we have, and testing some of our assumptions about how these proxies are related to the climate variables of interest, and I think one of the particularly useful ways that pseudoproxies come into effect is that you can do things like play around with the amount of noise in the climate system. You can play around with the signal to climate, the signal to noise ratios in the climate variables, and see what impact that has on these reconstructions. And that's a really important tool that often has a really profound influence on the reconstructions that you get out of it. So in this particular study, they were going through this type of framework. Okay, so now touching on proxy system models. Excuse me for a second. Okay, so one of the issues, not one of the issues, but one of the challenges with proxy records is that they're often difficult to interpret because they typically represent nonlinear, multivariate, biased, and noisy recorders of the climate system. And traditional paleoclimate reconstruction approaches have often relied on things like empirical calibrations between the measured variables and the climate variables. And sort of that framework is known as inverse modeling of the climate proxy relationships. And it sort of aggregates all of the various sources of uncertainty associated with those relationships into one thing. And it is very difficult to tease apart. But an alternative and sort of complementary approach to that is to predict the measured value of the proxy based on the environmental forcing and the processes that are operating within the proxy sensor and the archive. And so that's known as a forward modeling approach with a proxy system model. And so they really, I think one of the real advantages of proxy system models is that they allow for real mechanistic understanding of the physical and chemical and biological processes that underlie our proxy records. And they're generally idealized representations of these really complex proxy systems, but they allow us to test whether some of the commonly held assumptions made in inverse modeling are really valid. So things like assumptions of stationarity and linearity and those types of things. So I think I've included some examples of studies that have focused on proxy system models below here, and I would encourage you to look at those for more information. But I'll go through a couple examples here. And so one is PRYSM, which is a open source Python framework that Sylvia D has developed for a number of different types of archives. But the most recent one, I think, is a proxy system model for lake sediment records. And so just kind of to walk you through how this framework works in this context, the environment here would include things like lake temperature, evaporation and precipitation, lake depth, and the water isotope values of lake water and the precipitation and runoff. And the sensor model includes a variety of different sensors. Here it's the hydrogen isotope composition of leaf waxes and the oxygen isotope composition of carbonates, among other things. And then you have the archive model, and that really determines how those sensors are incorporated into the sediment record and undergo processes like sedimentation, compaction, bioturbation, which is really important to what you end up with at the end of the day and the measurements that you're actually making on that proxy system. And so then you have the observation model, which you can do things like look at how dating uncertainties affect your reconstruction target and how things like analytical uncertainties play into it. And so the proxy system model incorporates each of these different components and is therefore a really powerful tool for trying to sort of develop this sort of mechanistic understanding of our proxy systems. Okay, So I think proxy system models are really useful for things like, I don't think people have in great length about how the value of proxy system models for things like designing optimal sampling networks for paleoclimate reconstructions, and I'll show an example of one of those in a minute. For improving data model comparisons, so putting sort of our proxy records and our models on par with one another, and developing a process level understanding of the proxy systems, and also applying these models to observations. We can apply them to models, but we can also apply them to observations to test the consistency of some of our commonly held assumptions in our proxy interpretations. And then they are also really useful for quantifying the total uncertainty in the response of proxy systems to this climate forcing, and to really parsing those uncertainties apart and having a better understanding of where they arise from and what their contribution to the total uncertainty is. Okay, so here's one example. This is from Michael Evans' recent work. And in this case, it's looking at developing a proxy system model for looking at oxygen isotopes, for developing designing an optimal sampling network for oxygen isotopes in tree cellulose for the purposes of reconstructing tropical sea surface temperature variability. Okay, so I won't go into too much detail, but I'd like to mention the existence of paleoclimate data assimilation, because I think it's really an emerging and really powerful emerging tool of these paleo data model comparisons. And so how it works is that we start with data assimilation starts with a prior estimate of the climate fields to be analyzed. And this is often taken as a random sample from a model climatology, or can be from an unforced model simulation. And it's updated using the difference between proxy records and this prior. And in order to estimate the observation of interest, it incorporates a forward model, like we were just talking about, to map the climate variables to the measurement. And what it really, I think its real power is in it really fills, how to say this, it really provides sort of dynamical context to these paleoclimate reconstructions, of course, within the limitations of the dynamics that are operating in the climate model. But it allows for climate fields to be simultaneously developed. So for things like you can assimilate paleo temperature information and get out precipitation, for instance. And it uses these dynamical models to really infer spatial relationships between these climate fields. And so this really provides a dynamically consistent reconstruction, again, within the dynamics of the model, be they biased or not. Yeah, okay. So one of the most recent, oops, there it is. Okay, sorry, this is moving for me. Okay, so one of the most recent examples of this is the last Millennium Climate Reanalysis project. that a number of people have been involved in over the years, but I think Greg Haycom is really spearheading. And so it's trying to do this through the last millennium, and so primarily through temperature proxy reconstructions, but melding temperature reconstructions with climate models to better constrain temperature variability over the last millennium. And so, yeah, I won't get into this too much, and I don't claim to understand the nitty-gritty of all of this, but it's a really interesting and powerful tool that I think is really changing the way that we'll be able to make some of these data model comparisons in the future. Okay, so let me provide a few examples of sort of just going through the spectrum of these tools. So the first is, this is work from Julien Millet that looks at multi-proxy reconstruction, two different types of multi-proxy reconstruction methodologies on a network of high-resolution paleoclimate records from the tropics, and evaluates their performance in reconstructing SST variability in the central tropical Pacific over the last millennium. So the target here, it's hard to see in this figure, but the target here is the Nino 3.4 box, of which there's no proxy records that actually appear in that box. So yeah, the idea here is really to rely on these temporal and spatial relationships and teleconnection patterns to inform a really important component of the climate system, but in a region that we have few proxy records even for this relatively well-sampled period. And so, yeah, he sort of talked put forward a number of interesting conclusions from that work. But I think one of the real challenges he raised was that multi-decadal to multi-decadal variability is really different in these reconstructions than in the couple GCM simulations, and that this sort of centennial scale variability is really poorly constrained, both due to uncertainties in instrumental tropical Pacific SSTs, and also to the lack of long high-resolution paleoclimate records from the central and eastern Pacific. And so this sort of highlights where perhaps we should be looking to bolster our proxy data sets, and thinking about, yeah, priorities for improved tropical Pacific sea surface temperature reconstructions. Okay. So next, I just wanted to highlight Diane Thompson's, some of Diane Thompson's work, looking at comparing, looking at changes in the tropical Pacific mean state and ENSO variability over the 20th century, and comparing that between proxies, observations, and coupled models. And so on the left here, this figure is looking at what you can think of as a tropical Pacific mean state on the x-axis versus the SST variability on the y-axis, and incorporating a suite of coral records, which is in the little asterisk star, versus a suite of coupled climate model simulations. And what comes out of it is that their work really highlights some substantial differences between observations and the simulated coral trends over the 20th century. And it suggests that there's potential biases in models, and particularly they highlight model simulated salinity fields, and they suggest that the responsive tropical hydroclimate to 20th century forcing needs to be better investigated to improve our understanding of the tropical Pacific climate. And so I'm sure Sam can speak far more to this than I can, but this is just showing an example from some of her recent work that looks at using the isotope-enabled regional ocean modeling system, ISO-ROMS, to look at the dynamics of seawater delta 18O and salinity variations associated with El Nino and La Nina events during the 20th century as a way to kind of test the reliability of some of our coral-based estimates of ENSO. And so my understanding of this, of her work, is that it really highlighted that some of these assumptions may not be valid, and suggested there was a real need for a dynamical understanding and more sustained in situ observations of seawater isotopes and salinity in the tropical Pacific to better understand our proxy systems. Okay, next I wanted to talk about how, I guess it's sort of along the same line, thinking about how some of our modeling frameworks and theoretical frameworks can inform previously, in this case, fairly long-held assumptions about what our proxy records mean. And so this is a figure from Francesco Posada's paper, David Battisti, that has sort of since been developed in the same conclusions that sort of come out in a number of different ways, looking at reinterpreting changes in the Asian monsoon from Chinese stalagmite oxygen isotope records. So the Speleothem oxygen isotope records really represent some of the most detailed information into past changes in Asian summer monsoon variability. Long, high resolution, and there are a number of reconstructions generated across sort of the Asian region now. But we still really lack critical understanding of what these oxygen isotope composition of these speleothems represent in terms of large-scale shifts in the monsoon circulation versus more local-scale changes in precipitation. So the sort of traditional interpretation has really linked these oxygen isotope variations as a proxy for East Asian summer monsoon strength or intensity, but others have really interpreted it as reflecting changes in anything from the fraction of water vapor retained during a rainout of moisture trajectories, the sources of the moisture sources, and the seasonality of the precipitation. And so this paper in particular was looking at, I think was looking at Heinrich events, but really suggested that what we were seeing in central China was a reflection of what was actually happening downstream or upstream in the Indian monsoon region, and really suggested that some of these long-held beliefs should be reevaluated within the context, and could only really come about through these tools like isotope-enabled model simulations. So there's sort of a collection of other papers on that same topic. And then finally, I just wanted to point out, I think this is a really nice paper that has come out recently by Tripti Bhattacharya that looks at causes of drought during widespread Mesoamerican drought during the Medieval Climate Anomaly and potential sources from North Atlantic SST variability. So yeah, I won't go into detail on this, but she sort of compiles some really some more sophisticated sort of statistical frameworks for comparing these multi-proxy reconstructions of hydroclimate variability from lakes and speleothems and marine sediments, and looks into the really looks into the timing of this large-scale drought, and also looks at the mechanisms by pulling in climate model simulations. So I would refer you to that for kind of a nice example of how those things are brought together. Yeah, so that's really what I wanted to touch on, just to kind of come back to the original framework. I think that we've seen real notable improvements in our proxy development and paleoclimate data model comparisons through a number of different pathways that have included the relatively rapid increase in the couple of climate models that have water isotopes, as well as the development of proxy system models and pseudoproxy experiments. And I think we're seeing new and innovative ways that those are being are still being developed, and are still being developed for a number of different types of proxy systems. So there's yeah, I think we're starting to see a more full spectrum of, instead of just being developed for like temperature records and tree ring-based temperature records. There's really widely available proxy system models that, again, are open source and are available to the broader community, and so are able to be folded into these model data comparisons in a more comprehensive fashion. And then paleoclimate data assimilation techniques are really an emerging tool that I think will provide a lot of novel information from proxy data and climate models, and help to put kind of our models and data on the same playing field. So I'm excited to see where this all goes in the future. But I hope I've given you guys a lot of resources to look into all of this. I know I just kind of walked through this very quickly, but that's sort of the perspective that I'm coming from in terms of proxy data comparisons and what I do and think about in some of my work. And so, yeah, I hope it provides a good resource for our discussions moving forward.